Actually, I want to show another example of a generalized algebraic theory.
Oh, yeah.
Which is the simplest, the simplest Turing-complete programming language is the SK combinator calculus by Moses Schoenfinkel, and actually it was the earliest such language from early 1920s. Schoenfinkel was Hilbert's PhD student, and he invented this as a way to eliminate variables. They didn't understand back then, and then this to eliminate variables via combinators. That was the idea. So the nice version of this is the simplified combinator calculus. So this is a model of simplified combinator calculus. It has types, which are a set, and then it has terms, which are indexed by types, just like the Razor language yesterday. And okay, so we have some base type, and then we have function type, function application. So it's a term of type A arrow B, and the term of type A, then we get a term of type B, and then we have the two combinators K and S. So K is a term from A to B, A. And S is a bit more complicated. So if you have a function from A to B to C, and the function from B, what is it? A to B, right? A to B.
And then A to C.
Then you get a function from A to C. Is this correct?
Yes.
Yes.
Close the parenthesis.
Okay. And then, yeah.
Close the parenthesis.
Thanks. Okay. And then we have two equations saying that if I apply K to A and B, I get back A, and I have S beta. If I apply S to F and G and A, then I get back F applied to A, applied to G, applied to A. Okay, so here already I use lots of notational conventions. So for example, application actually has 4 arguments rather than 2 arguments, right? The A and B are implicit arguments here. Okay, so if I'm really precise, then I have to write the other 2 arguments here, but I don't for convenience, and then I can use the normal infix application. And similarly, K and S have, so K has 2 implicit arguments, okay, and S has 3 implicit arguments. And K beta, how many implicit arguments does K beta have? No, not 2 is a good try, but it's wrong. 4, right? Because the A and the small a, small b, and the big A, big B. Okay, and this has even more. Okay. Yeah. Right. And then, so I never met anyone who was able to program in this language. I mean, other people are just cheating. They program in lambda calculus and then they translate it to combinators. But it's very nice because it's really, really simple. And so for a example program that we can, so, you know, if we do derivable things, so we derive something in this language, then we can derive the I combinator, which is just A arrow A. So this is derivable. This also works for every A. Okay, I don't know how to invent this, but if you try enough, you can invent. It's not very big. I just remember the definition. The definition is S applied to K applied. Okay. Yeah, you know, one more convention which is usual. It's the same as in lambda calculus. So the dot is left associative, and the arrow is right. Usual, the same thing here. And I mean, if I look at this, I'm not even sure if this makes sense, and I don't know if it has this time. If you need to be, I mean, you need to figure out all the implicit arguments and that they are met. So this is really concise notation, and you don't know. I mean, You don't, if you do this in Agda the same way, Agda, what do you think Agda will do here? What color will this be? Either red or, okay, no, it's not red, because red is only if there's a termination argument, right? No, it's also red underline if it's not well typed, but this will be yellow, because actually it's not completely clear what the implicit arguments are. Okay, so I mean, you know, we discussed that the terms in this. I mean, what are the terms in this theory? If we forget about the types, then they are binary trees, right? Where this is the leaves are K or S, right? And then you have these two equations, which, for example, K says, what the first one says, that if you have this situation, here is some A, here is B, then this is the same as the A, right? This is what the equation says. So there are these trees, and then the equations say that some of them are identified. But actually, this is not a very good notation, these syntax trees, because you can't see how whether the types match. So this is why it's nicer to write down these terms using derivation trees. Okay, so derivation trees, I view them as just, first of all, derivation rules are just notation for the same thing as this. So you can write down these things in a way that you anchor all the functions. Okay, and then if you anchor the functions, then there's only one arrow left, and instead of arrow you write horizontal line. Okay, so for example, this rule is turned into, if you have an, and you give a name to everything. If A is a type, B is a type, then you get A and B, which is a type. Okay, so this is just a different notation for this line, and some people like this more. Or let's see, this one is more interesting, right? So if I have some F, which is a term in A or B, then I have a small a, which is a term in big A. Then I have F A, which is a term in B. So do you see the one-to-one map between the two notations? Okay, so when I write this, I don't mean any kind of kernel relation or binary relation between terms and types. I just mean this. Okay. In our meta theory is dependent type theory, so you can have dependent types, and some people like, there was even a proof assistant programming language which had this two-dimensional notation. Who remembers it? Yeah? Yeah. Yes, it was epigram. So Conor McBride's proof assistant had famously this two-dimensional syntax. So actually you could write it this way, and you didn't have to write this way. Was there a question?
Yeah, I was wondering, because you can also have nested bytypes on the left, you get some kind of nested sequence.
Nested bytype. So first you have to anchor it. So actually there's a step in between. So first you do this. Sorry, what was this? Arrow. You say time times time, arrow time. Okay, and then you can go here.
You have, for example, so if you have a lambda f, for example, then you have a function on the left. You can go deep. Yeah, maybe this.
Okay, no. So currently we only allow generalized algebraic theories. So what does it mean? That basically all the arguments and all the consequences, all the results of all the functions, they have to be one of the sorts. Okay, so they can, yeah. So there's really this actually this notation is quite nice because this enforces this restriction that you cannot write crazy things like here. I cannot write something like F goes from type, something like this, right? This I cannot write, and this notation is good because this enforces that you cannot write this. Why this notation doesn't, but this Agda or Kokak says this. Okay, so now this notation is nice because now we can check whether this really makes sense. Okay, if we rewrite all of this using this notation, so let's just see. So if I want to say SKK, I want to show that this is the term type AROA, right? Then I use this modus ponens rule, and then I need to know that S composed with K, S composed K is the term of some A arrow that thing, so some type arrow A, okay, and K has that type. Okay. K has the type that I write here. Okay, so here I have so K in general can have, so this the implicit argument I just write B and C. So I don't know if this can be a B arrow C arrow B, right? So this could be B arrow C arrow B, right? At this point, this is good. Okay. So now here, so this is fine. This is already this rule written in the derivation rule format. While here I use another application. So S needs to have type. What's the type of S? So S needs to have type some. Okay, again, I write the same way. So something arrow this thing, right? So I write B arrow B to A arrow A. While K, now I write it above it as a list of arguments. So K needs to have this type, right? So K, again, most generally, K can have arguments D and E. So it's D arrow E arrow B. And then this is D arrow E arrow D. Okay, so K is fine. But now I need to check that F really complies this rule. So I will do some unification, and I will have to realize what these arguments have to be. So this is the general, okay, maybe it's a bit unreadable. This is the general shape of S, right? So from the return type, I learned that A is the same as C because it's A arrow A, right? So where does A is fixed, okay? So A appears here and here. So I learned that D is the same as A, right? Because D appears here. So first of all, I replace D by A in every place. Okay. Sorry, I did something stupid, right? No, I just did this. So so I check that these things are the same. Now I'm also checking whether these things are the same. Okay, so the first, so this input of the second function, where there is B, it has to be A. So all the B's also have to be A's. Okay, A and A. Okay, so then here I see that this B has to be the same as this B, right? So this E also has to be A. So the E is A.
So it's actually C to A.
Sorry?
That's the C arrow A, right?
Yes.
Because the second argument
That must be C to A.
yes, C to A.
Oh, sorry, yeah. So I made a mistake in the. No, I just made a mistake right now.
That's the final thing.
Thanks. Okay. Yeah, right. So this is the return type as the second thing. So the B is CROA. So this has to be CROA. Okay. So then the E is CROA. So let me just write this again. So this is A R CROA, right? A. And then here, this one is also A arrow A. Okay. And then there's no other constraint. So now I see why it is yet, because what is it? So the one of the implicit in the second implicit argument of this K, this first K, I have freedom to choose C to be anything, right? So actually there are lots of different identity functions corresponding to this. Okay, so this was a okay, and yeah. So if I want to be, oh yeah, here I forgot to write. Also here I forgot to rewrite what these were. But, okay, I don't know, something. It doesn't really matter. But this way you can, and you know, the type checker on some lower level does this kind of argument when you actually do this. Yeah.
C should to become A. It's the return type of S. And so the rest type is A.
Why does C need to become A?
As the rest type of S. 3 arguments then C. So that's A.
So C only appears here and here, and yeah.
Oh, okay, no.
So
That's fine.
and then in there, so I think there's some information which is not important. Yeah. So okay. So actually, I don't know what is the nicest notation for typed combinator calculus. Like if you do full annotation, then the K and the S also have all the A and the arguments always returned, but then there's duplication. So I'm not sure what is good pre-syntax, so that you don't have too much extra information. Yeah. Okay, and then so what we check is that this certainly makes sense with some choice of C. For example, C can be A or iota or whatever, and then we can check whether this really runs as we expected. So this was the programming part. We wrote a program in combinator calculus, and now we run the program. So we check whether if I apply the I to some A, then it's really the identity function. So this is what this means. And now we do algebra. So we just take the equations and apply them. So right, the S beta says that this is K applied to A, right? Applied to K applied to A, right? And then we have K beta, which says that if K is applied to 2 arguments, then we, yeah, and then we get like this thing. Okay, so this is how we program in a simply typed combinator calculus. So we looked at models, what is derivable, and then now we look at the standard model, just as we looked at yesterday for the Razor language. So the standard model is the same. So types are just sets. Term A are given by elements of A. Iota is some parameter. It can be any set, and then the function space is given by method theoretic function space. And then we can implement K as the constant function and S as the function which implements this. Right? So like S is given by the function, which takes method theoretic lambda, an F and G and an A, and it returns F. Oh yeah, this is method theoretic application, right? This is space. Method theoretic space, right? And this returns FAGA. And so very important that here I didn't write dots. Okay, so this is what you have to appreciate when you write these things, that there are no dots here, right? And okay, and then 2 more general notions that you like to think, check for languages. It is consistency, yeah?
What is iota in the standard model?
What is the?
Iota?
Iota is a parameter. Iota is just a set. So iota is actually a parameter of the standard model. Okay, iota is some set. If that you can choose to be anything. We will choose it to be 2 different things for the 2 different consistency proofs. So you can say that, what does it mean that theory like this is consistent? So first of all, it can have, there is logical consistency, which says that one of the sorts of this theory is empty. Okay, so there either exists a type which doesn't have any, also either type is empty, or there exists some type A and such that TMA is empty. Okay, so this means that for theories with type and terms, usually you want that there are some types which don't contain any elements. Like if that's why it's called logical, because logic, like the false proposition, shouldn't have any proofs. So here, one of the types shouldn't have any elements. So there exists a type AI, which is a type in the syntax, okay, in the initial model, such that TM AI is empty. So I write it like this. Okay, so if it has an element, then we get an element of the meta-theoretic empty type. Okay, so how do we prove logical consistency for this theory? So consistency is usually just proven by the standard model or some easy model construction for all of the theories. How do you prove this? So we just interpret into the standard model, okay? Into the standard model where, so this is interpret into standard model where iota is the meta-theoretic empty set, okay? So this is a parameter of the standard model. There's no requirement on what this parameter should be, okay? And then we choose, we say that AI should be iota I, right? So the syntactic iota type. And then from the interpretation, from the standard model, we get a function, you know, we get, first of all, we get a function from I to pi in the standard model, but types in the standard model are just sets, as we said here. Moreover, we get a function from PMI of the AI to, okay, let's call this, what do we call this? I don't know. Okay, let's just call it double bracket. Okay, that's a good name for all kind of semantic interpretation functions, right? So this double bracket is a morphism, right, from the initial model to this model. Okay, so okay, maybe I write down the whole type of double bracket again. So what is a morphism from the initial model to some other model? First of all, this one. And second, this is like the pi component, then the term component of this will be termed in the standard model at the interpretation of types, right? So this is also a recursive function, because the second function for the morphism depends on it's like mentions the first function, right? To be able to talk about what the terms are interpreted to, we already know what the types will be interpreted into, okay? And we know that this is a homomorphism, so it's a morphism, so it preserves all the operations. So in particular, we know that iota will be this iota parameter standard model, and yeah, maybe that's enough for this consistency proof, right? Because yeah, okay. So then what do we get? So types in the standard model is set. Terms in the standard model are just the interpretation of the type. Okay. And iota is just iota of standard model. So assuming there is some A, some B, I, which is a term in iota of I, if we interpret BI, the standard model, we get an interpretation of iota I. Interpretation of iota I by this equation is the iota in the standard model, which we set to be meta-theoretic 0. Okay, so we proved the logical consistency of this language. Okay, any questions about this? Okay, so then we prove equational consistency. So that means that there are two different syntactic terms which are not equal. Okay, So actually for equational consistency, we can look both at types and terms. So the equational consistency of types is also easy to prove, no? For example, you just define a model in which types are given by meta-theoretic pool, and terms are given by meta-theoretic unit height, okay? And then iota is mapped true, meta-theoretic true, and arrow is mapped to meta-theoretic false, and then that's how you can distinguish the two, okay? And how do we do the same for terms? How would you do show that there are two terms which are not equal, two terms of the same type which are not equal? Any hints, ideas?
Sorry, I'm a bit confused by the definition of consistency. I don't see how it's going to.
So yeah, okay. So more formally, there is a AI in TI and A and A prime in TMI AI, such that A is not equal to. This is what we want. There are two terms which are not the same. How do you? So this is an equation of consistency. I mean, for example, if we choose the big AI to be iota I, that's not good because we just proved that there are no terms of that type. So that's we won't be able to come up with the small a and small a prime there. So what shall we choose for big AI? Just think about the simplest solution using this standard model. Yeah, very good. So what if I choose iota in the standard model to be meta-theoretic element set, okay? And then we just need a function which distinguishes two different arguments of two. So maybe if, and now this is the usual cheating. So what if I want to get some A such that interpretation of A into the standard model is this function lambda x y dot x, okay? And A prime, I want it to be this function lambda x y dot y. Okay? You think these are definable?
The usual abstraction definition.
Yeah. So we just need to come up with some combinatory terms which implement these two functions. Okay. Sorry?
The first is already clear.
Yeah. The first one is not that difficult, right? Because that's just k, right? Okay. So we see that this is k. Okay. And k where both arguments are iota, syntactic iota. Okay. And then if we interpret that k into the standard model, then we will get this function. Does everyone see this? Okay. Yeah. And now we need to come up with some combinator. We won't think about it now because there's not infinite amount of time. But you can ask ChatGPT. Probably ChatGPT knows the bracket abstraction algorithm. So the bracket abstraction algorithm is to show that you can define lambda in this theory. Okay, there are some subtleties there. Actually, you cannot define lambda in this theory. You need some more equations to be able to do it. Okay, so once you have this, right, then if we assume that this k is equal to this A prime, then that if they are equal, then their interpretation into the standard model are also equal by congruence. So then this function and this function, which are polar functions, are also equal. And if you apply true and false to them, then you get that true is equal to false. Okay. So this is the standard way to. Okay. So now we have this nice language which is equationally consistent. I mean, if we erase types, then this is a Turing complete. Then this becomes Turing complete, right? and then it's much harder to equational consistency. Then okay, then it's really difficult to give a non-trivial model. So because there's no finite model where this model doesn't work because we don't have types and we have to interpret every term in the same some kind of type that we need to come up with, and it's quite difficult. Okay. Okay, so now I will show how to prove normalization for this language. Maybe I just first write down the induction principle. Okay. So remember that the induction principle for any language says that for any dependent model, there is a dependent morphism into that dependent model. So over the syntax. So what is a dependent model over I of this language? Okay, so we have a tie component, which is tie I arrow set. Yeah, so the dependent model is also called the motifs and methods of the elimination principle, or the induction principle, or structural induction principle for this language. It has a TM component, which says that if I have tie of some AI, and then a TMI AI, then I get a set, right? So this is what types will be. Syntactic types will be eliminated into. This is what syntactic terms will be eliminated into. Then I have a iota component, which is a tie at iota I. Okay. So maybe for readability, I put a T here. So a dependent T is a dependent model over I. So then I need to decorate all of these with T components. Okay. Then I have an ROD. Right, which says that if I have a tie D over some syntactic A and a tie D over some syntactic B, then I get an element of tie D over the syntactic function type. Okay, this also has AI and BI were implicit arguments. Okay, the application has even more implicit arguments. So if I have a TM D over some A or B, okay, of some Fi, then I have a TMD of some A of some AI, then I get a TMD at B of Fi syntactic application AI. So beware that here this AROB is, sorry, should have these everywhere, right? So this ABROBB is this ROB, right? Where the AB is something over AI and the BD is something over BI. Okay. If you're very consistent with naming of the meta variables, then it's everything fits together nicely. But yeah, so currently I don't think there's a proof assistant which forces you to give good names to your meta variables in a consistent way, and probably it's not even possible on paper sometimes. But yeah, I don't know theory of meta variables. Okay, then the KD, it's quite easy to write the KD because I just write TMD, AD. I just put the D's everywhere. I do this, I just put the D's everywhere, and then here I just write KI, and then there are lots of implicit arguments. Okay, and then I also have an SD which is similar, and then two equations. Okay, now I don't write down everything. Okay, and then what does induction say? Induction. So I get a type component of induction, which says that if you have some syntactic type, then we'll get a semantic type, which also depends on the syntactic type. And then there is a term component that says that if you have a syntactic term of type A, then you have a semantic term where the semantic type is given by the induction on the type applied to AI, and then the term depends on this one, okay? And then you also have computation rules that it computes properly, like a homomorphism, okay? So to define normalization, we first need to decide what normal form should be. So who knows what are normal forms for this this theory? So you can, the K and S beta, they are quite simple rules. They can be treated as rewrite rules. So actually it's quite easy to guess what the normal forms here, because it's a, this can, yeah, this kind of, so now we don't know that this has a direction, right? These are not rewrite rules, these are just equalities. But you can, this theory also behaves very well with rewriting, and you can prove confluence and stuff, and strong normalization. But but we don't care about this. We just consider those things equal, and then normalization is specified just as yesterday, that we just have a notion of normal forms, which are separate from the syntax. So the syntax, right? It's not clear that it's, for example, it's obviously if you get two terms, whether they are equal. Okay, so that's or not equal. It's not obvious how to decide whether they are equal or not equal, because there are these equations. Maybe you have to use the equations in some tricky way, combine them, get a proof of equality. Okay. And how do you know that there is no possibility of combining the equations such that they become the same, right? So what we want is to prove that the syntax of this theory is actually isomorphic to some other syntax of some other very simple theory which doesn't have equations, which is not quotiented. And if there are no quotients, then you can always look at the normal forms and compare them structurally. Okay. So, for example, if you are able to show that this theory is isomorphic to natural numbers, then it's very easy to decide equality of natural numbers. Okay. And okay, so here the idea works that you just look at the terms and you say, well, I want all the kinds of terms that I can build using K and S and application, but I just want to exclude this possibility and I want to exclude this possibility. Okay, so what are those? So you can have, so K is fine, that's normal form, right? You cannot apply it to anything. Okay, then, okay, maybe I write it here, K. Okay, then also I can write K applied to some A, where A is already a normal, right? That's also good. But if I have K, A, B, this shouldn't be a normal form, okay? So I just exclude this. Okay, then I have S, that's normal. Then I have S applied to some F, then I have S applied to F applied to G, and that's it. Where F, G, and these are normal. So this is the inductive definition of normal forms. Okay. So if we are able to prove that every term is equal to one of these, then we are done. Okay. But actually, we have to be a bit more careful, because this is all typed and stuff. And what type is this? So let's do it a bit more precisely. So now this was my theory SPCC. So now I define the theory SPCC normal forms. Okay, this is the new name for another generalized algebraic theory. Let's call it NF. Okay, the carrier of this theory will be NF, which will represent terms in normal forms, and NF will be indexed by syntax types. Okay. Some AI, which is a type in the syntax, but not only syntactic types, but I also index it by syntactic terms. Okay, term AI are set. Okay, this is a algebraic theory. Actually, it's not a generalized algebraic theory. It's just a multi-sorted algebraic theory. It only has one sort, NF. Okay. And it's parameterized with multiple things, just like vectors or vectors of Boole. they are also a multi-sorted algebraic theory because there's vector pool of length 0, vector pool of length 1, and so on. So they are indexed by natural numbers, which is some pre-existing thing. So this is also indexed by some pre-existing stuff, but the same things that you can do with GOTs, which are not indexed by pre-existing things, you can also do it with GOTs, which are indexed by some pre-existing things. And then let's call this this operation K null, which says that I have an element of NF of AI rho I EI rho AI, and then so the first index is a syntactic type, and the second index is a syntactic term of that type. Okay, and then I have K1, which says if I have NF something of A, then I get NF something of K I by A. Okay. So the K1 takes underscore is some type that I don't want to think about now. Right? Is you have a normal form. If AI is in normal form, then AI is also in normal form. Okay. And then I have S0, which does that. Syntactic S is in normal form. S1 says that if S has one argument with normal form F, then normal form something of SF, and S2 says if normal form M and normal form G, then normal form this. Okay, and imagine all the I pieces. Okay, so what we did, we defined a new algebraic theory. We call this STCC normal forms. So the carrier, you can think about this as a predicate on terms. Okay, so this is not like a separate type, but if this predicate holds for some syntactic term, then you know that it is a normal form, right? And then now our goal is to prove normalization in a way that in the end I get a function which from any term, any syntactic term of any type gives you that the term was already in normal form. Okay, this is our goal. And for very simple theories like yesterday, you can just prove this normalization by induction on terms directly by one induction. And this theory has higher order functions, and you cannot do this anymore. And you need to use this idea, which I think it was originally by William Tate, who died like 1 or 2 years ago, quite recently. And the idea is to use logical predicates or logical relations. It's also called, I don't know what's the relation to the reducibility candidate method. That's probably also the same. So here, I think this is the proof that I will show is the simplest presentation of the states idea, because this is a very simple theory and the proof is also very simple. Okay, and so actually it's not enough to do, okay, and it's quite easy to see why it's not enough to just do an induction on terms. So what if I just want to define this directly by induction on terms, which means that I just define a display model where I don't care about types, I just do induction on terms, right? Then which is the operator, and so what I want to, okay, what I mean is that I want to say that TMP of some AI, and I don't care about this argument, okay? I care about the AI, and I don't care about this argument, and then term AI, and then I just define is that this is already normal. And this is what I want to do. Okay, so if I want to do this, where does it break? Which operation is the one that I cannot define? I mean, there's not that many. There's 3, right? So K and S are actually fine, right? Because K in this model, I can just define K in this D model by just K0, right? K0 says that K is already in normal form, right? What do I need to give for K? I need to say TMD at Ki. Now I ignore this for this TMD Ki, and TMD at Ki just says that K is in normal form, so it's K0 as these. and 0. Yeah, so obviously I cannot define application because it's difficult to define application for this, right? So because application needs to like investigate whether this thing is okay applied to something and then compute further, but there might be more computations here, so it's really not clear how to do this. Okay, so then let's follow Tate's idea, and he said, okay, I have to do it here. So he said that, and actually it makes sense that you cannot do it just by induction on terms, because then why are types there, right? And we know that for untyped combinatorial calculus, there's no normalization. Equality is undecidable there. It's Turing complete. So there's, yeah, so we really need to use the type information somehow to yeah, okay, and this is the idea. So type of some AI is defined as a logical, as a predicate, as a proof relevant logical predicate on terms of type A. Okay, so this is not exactly how Tate originally formulated it, but I say that there is a PA, okay, I call it PA because it's a predicate on A, which is a family of sets over terms of type A. Okay, and then the idea is that but this is still not enough. So what I say is that, so the idea is that I define a predicate on every terms, for every type, a separate predicate for the type. And then I also define by induction on types a reify function, I just call it R of A, which says that if the predicate holds for some term, then actually the term is in normal form. Okay? AI of AI. Okay? So instead of directly trying to get the normal forms, okay, I say that I first define the predicate on types, and then once I have that the predicate holds for a particular term, then I get the normal form. Okay, and then what do I say for terms? For a term where the look what I need to give for terms. I receive a witness for the type. Okay, so what is a witness for the type? Well, I have a logical predicate for the type, and I have a reify function for the type. Okay, and then what for the term? What I want to say that by induction on terms, I show that the predicate holds for every term. So here I just say that the PA holds for this term. Okay, and once you once you have this setup, you still need to know how to do it for the function space, but then everything fits together, so it's quite easy. Okay, so but let's do it line by line. So what is iota? Okay, so what is iota? Well, it's two components. It's a predicate in terms of type iota and the reify function. So what should be the predicate? Okay, so iota. Let's just take, it's a type of iota I, right? So then I need a predicate on terms of type iota, okay, so I of type iota, and here I need to say, I give a set, right? And here I get an element of this set, and then I need to return a normal form of type iota. So what should be the set? So what does the logical predicate say about terms of type iota? What do we already established something about terms of type iota using a previous model, the standard model, right? Yeah, there are no such terms. So we say that the predicate says that there's no such term. Okay, so we just return the meta-theoretic empty type 0. Okay, but then it's quite easy to define a function from the meta-theoretic empty type. I mean, this is the alpha notation or x-falso or whatever. There's no element of the meta-theoretic empty type. Okay, so we treat it iota. And we can do this because really there are no termformers which mention iota, so I won't get into trouble later in defining the dependent model because iota is not mentioned again. Okay, so okay, then what about function space? So I have a predicate on A, I have a refi for A, then I have a predicate on B, I have a refi for B, okay? And now I need to give a predicate on A arrow B, predicate on the functions. So here I have a fi, which has type term I from AI to BI. And I need to return a set, just like here. And then I need a refi function. Okay. So it will need some more space. So here, and this is another important bit in Bates' idea, is that he said that for functions, the predicate should say, this is a mantra that I remember, maybe there is some deeper insight on how to come up with this, but I only know the mantra that the function preserves the predicate. That's what we need to say, okay? So if the type that we get is that if there's the PA holds for some input AI, okay, then PB holds at FI applied to AI. Okay, that's it. This is the predicate that we say, but then we also need refi, and it's not clear how we get refi from this. So here there's a simple trick that I just say that, well, the predicate for function says that the predicate is preserved by the function, and it also says that FR is the normal. Okay, AROB, ARYBI. Okay. So it's two components. The predicate actually has two components. First of all, I say that the F preserves the predicate. Second, I say that it is in normal form. And then the refi is quite easy. It's just second projection. Fine. Right? Because if P of ARO is so for some Fi, then it gives me the preservation of the PA and PB, and also that Fi is in normal form, so refi just projects it down. Okay. So okay, so let's maybe let's do application first. Okay, so if I have a call this okay, P of F applied in B to P of A, right? So okay, let's just read what I need here. So I need the component for terms at F and the component for terms at A, and I need the component for terms at the application. Okay, so P of F has type what is this, TMB of A arrow B of Fi, okay, and then P of A has type sorry, I just immediately replace it with the definition. So this is just the predicate for A arrow B at Fi, and this is the predicate at A for AI. Okay, so that's PFN and PA, and then here I need the predicate at B of Fi applied to AI. Right? So I guess I could have invented what the predicate should be while looking at application. Yeah, because what I want is knowing that A satisfies the predicate and F satisfies the predicate, F applied to A satisfies the predicate. And this is exactly what the PA says, right? So the PAROB will have this component and this component. So I just use the first component in P of F, and I apply a P of A, and I'm done, right? That exactly gives me this. Okay. I mean, it's so, this is like very concise and very beautiful, I think, and you can count it. So now on we cannot mess up whatever, you can only write the right thing. So once you have written these lines, this is easy. Okay. Let's just do K, the component K to illustrate this, and check K beta, and then you can finish S at home. So what does K say? So K in P will have type, let's see, TMB of P for the type of K, and then refi, and then this. So it will be the predicate on A RO B RO A for K. Okay. So what is the predicate on A RO B RO K? Let's unfold this. It's written here. Okay. So this, if you do this, then like Agda or Kok helps you and unfolds it for you. So what I have is that if PA of AI, then I get P of BRA, K applied to AI, right? KI applied to AI. Moreover, I know that, maybe I write it in the next line. Moreover, I know that the original term, which had type ARO, BROA, was already in normal form. Okay. And we are still not done because this thing here again computes because this is a BROA. So what does it say? It says that for every PB of some BI, we get in PA that K applied to AI and BI. For this, the predicate holds. Moreover, we have a normal form of type BROA where K is applied to AI is applied to AI. Okay. So these are the components that we need to give. I won't write it down. Let's just convince ourselves that it is possible. So this is easy, right? That K is in normal form. We call it K0, right? So this one is fine. I underline it. Okay. Then then what else do we need? Well, we need this function here, okay? And we need that this is normal form, that K applied to AI is normal form. Let's concentrate on this. So this was K0, that was easy. This must be K1, right? Because this has that K applied to some AI. But to apply K1, I need that AI is in normal form. How do I know that AI is in normal form? Do I know that AI is in normal form at this point? And yeah, I'm sorry I messed up the bracketing. So here there should be a closing bracket, which closes this bracket, right? So I do know that the P relation holds for AI. Okay, so at the point when I need to prove that K applied to A is in normal form, I know that the predicate holds for A. Okay, but do we have refi? I can't see refi anywhere when I wrote here the time. Do you see the refi? Why do I have refi for A? Where does it come from? Why is it not on the blackboard?
Is it implicit somewhere?
Yes, exactly. So let's just go back here. So KD, well, for KD, the AD and the BD were implicit arguments, right? So actually, the KD has how many implicit arguments? It has 4, no? because it has AI, so the syntactic decay, then AD, which says that ID works for AI, and then the same for B. So actually here, when I define KD, I have the induction hypothesis for types, right? So this is really induction, just like induction for natural numbers. There's, for the successor case, I have an inductive hypothesis for the natural number. Here I have two inductive hypotheses for types. So I have both predicate for A, and which I'm already using, and reify for A, and predicate for B, and reify for B. Okay, so it's good. I can here use K1, and I just use reify for the AI. I can use it using this argument, and then I get this is normal form. Okay, and the more interesting bit, so this is also done. How do I get this one? Okay, so for K, I need to know that if the predicate holds for A and the predicate holds for B, then the predicate also holds for KAB. How do I get this?
Introduces to AI.
Yeah, exactly. We have the equation. Now we rely on the equation for K in the syntax, the I equation. So we know that actually, so now we make use of extensional type theory, which is our meta theory. I can rewrite this to AI, right? AI. No. And yeah, so and this is just a constant function. So it's quite remarkable that the proof of that the constant function normalizes semantically is just a constant function, right? I get two arguments and I return the first one. And when I need to prove K beta, what I need to prove is that the function lambda A B dot A applied A is the same as A. Sorry, applied to some B and A is the same as A. So it's definite. So K beta can be proven by just reference. There's no work need to be done. Okay, so if you want to redo this in Agda, there are some caveats, because to make sure that this constant function is well typed, you need to transport over this equation, right? This K beta equation. So to come with, because Agda doesn't implement extensional type theory, and then actually here the K beta won't be referred, but some transport mangling rule. But yeah, but on paper it's very nice. Yeah.
The equation for K beta is wrong. It's lambda AB dot A applied to AB.
The B and the A are switched up.
Yeah, thanks. Yeah. Okay. Okay, and yeah, so this is about, okay, now I just want to make some final remarks about GOTs and then to SOGATs, okay. Okay, so we've seen different examples of generalized algebraic theories and algebraic theories, and then I was mentioning induction and stuff, and you all know about inductive types, and there is this correspondence between inductive types and algebraic theories. Okay, so there are things called simple inductive types, like natural numbers or at least things like that. Binary trees, those in the algebraic theory words, those correspond to single sorted algebraic theories without equations. Okay, like natural numbers at yesterday, they are a single sorted algebraic theory without equations, but they are also simple inductive types. And sometimes it's useful to look at them as simple inductive types when you consider like pattern matching and iteration and recursion, defining functions by recursion. And sometimes it's useful to look at them as single sorted algebraic theories and then think about derivable and admissible operations and consistency and normalization and these kind of things. So usually you don't think about these when you you view them as inductive types. But if you have the both viewpoints, then it can be very beneficial. Okay, and so you know, so there's the inductive type, and then for inductive types, maybe you heard about initial algebra semantics of inductive types, or like algebras of an inductive type. And algebras of an inductive type are the same as as models of the corresponding algebra theory. Okay, so they are exactly the same. People just use different languages. Okay, and then if you have an algebraic theory, then you have models or algebras. Then the initial algebra is the same as the corresponding inductive type. Okay, right? And then here what you call iteration or recursion, that is called here the morphism from the initial model. Okay, here what we call syntax. I already said that the initial object here is also called syntax. Here we don't say syntax. We only talk about syntax when we are in. That's the inductive type. It's the syntax. Okay. Right. Okay. Let's just see more interesting things. So there are things called mutual inductive types. Okay. Or maybe simple inductive types are also called W types. Okay. W types, those correspond to single sorted algebraic theories, and there are index W types, and those correspond to multi-sorted algebraic theories, still without equations. Okay. Then there are the things called for mutual inductive types, they are also the same as index W types and index or indexed inductive types. Okay. These are the same. Okay, 1, 2, 3. Okay, so the next one is inductive types. Okay, so those correspond to generalized algebra theories without equations. Okay. Yeah.
When you say sorted, you mean as in an order relation? So like you're saying that single sorted have one order in the elements of the algorithm. There is nothing to do with that.
Sorry, Ken, I don't understand the question.
I mean, what do you mean when you say single sorted?
Oh, single sorted, I just mean that it's like monoid or ring where there's only one carrier. And multi-sorted is when there are multiple carriers, like category or I mean, STCC is more complicated than multi-sorted. So or multi-sorted is, I don't know, you could say vector spaces where there is the base ring or whatever, and then the vectors or
so single sorted is one carrier.
One carrier, yeah, just means one. Single sorted just means one carrier. Yeah. Okay. So inductive types are GOTs without equations. We've already seen GOTs. Okay, but now let's start from this side. So what is ordinary algebraic theories? What is the thing which corresponds in the inductive world? So maybe this wasn't as clear for a long time, because I mean these are not really well known here. So there are the QW types or quotient W types, or other name is quotient inductive type. Quotient inductive type. Okay, so maybe this like simple example of quotient inductive type is defining the usual definition of integers in a mathematics textbook, right? This pair of natural numbers with some equivalence relation, right? That's or the nicest definition with the homotopy type theory. You like to define integers where you have like natural numbers where you have zero and successor, but you also have predecessor, right? Which is the opposite of successor. But then you need to add two equations, right? And that's and then those equations say that zero and successor cancel. And then if you look at this more abstractly, then you can see that it's just a pointed set with an isomorphism. If you have very fancy type theory, you can even say that the integers are given by this set. Data integer is a set where you have zero, which is in Z, and then you have an equation set that Z is equal to Z. Okay, this is very weird because this is sort equation, right? So this is an equation with seconds, and this is, most proof assistant don't allow this. I don't know any proof assistant which allows this, but there could be proof assistant. So instead, what we do is we use univalence, and using univalence, we know that this is just an isomorphism, and then we can just list the components of this isomorphism, and those are the components that I just said: SOG, PRED, and PRED, SOG, PRED. Okay. Okay, so these are examples of quotient inductive type, and there's a PhD thesis written about quotient in QW types. Okay. Okay, and then what are generalized algebraic theories? They are called QIITs. So quotient inductive types, which are some, like Andy Pitt says that QIITs are probably the biggest invention in homotopy type theory. I don't know if Andre will confirm this, because this was a really big thing that you can now define real numbers abstractly and show as Cauchy sequences quotiented appropriately, and you don't need the axiom of choice to define addition on these Cauchy sequences. So QIITs give some kind of new choice principle, constructive choice principle into type theory, which was quite a recent invention. And maybe now we could rewrite Bishop's book in a nice, constructive, abstract way.
These are just set truncated hits, right?
Yes, yes. Okay, right. So you also have higher inductive types, and on the algebraic side, there are some higher algebraic theory, higher parts.
I mean, hits predate hits, and hits are a special case of hits. So
yeah.
I don't see how. I mean, maybe that what's important is that.
But quids don't have anything to do with univalence, but they come from homotopy theoretic inspiration.
But hits have nothing to do with univalence.
Okay, yeah. Okay, but still come from homotopy theoretic inspiration.
I mean, all this is saying is that Andy doesn't like hot.
Yeah. Yeah. Okay. Okay. Oh yeah, and the other general.
That's a question, by the way.
What?
Sorry, a question.
Yeah, so these higher gets don't have anything to do with higher order gets.
No, they don't have. They are higher in the sense that they can have operations which are not equalities, but higher equalities as well. Okay, so in these cases, for the higher things, we don't really separate operations and equalities, but equalities are also seen as some kind of higher dimensional operations, which give equation like paths rather than equalities. And there are very stupid paths which are just a point; those are the constructors, and then there are more nicer paths which are higher. Yeah.
We also have W types for index inductive types.
It's index W types. Yeah, there's a notion. Well,
yeah, but for inductive type.
No. So for inductive types, we don't have a nice small description. Right. So the issue is that it's the same for GOTs compared to algebraic theories. So to write down signatures for GOTs, you have to already have a setup of type theory. So I don't know of anything simpler than the syntax of dependent type theory that can describe GOTs or inductive types. It's the same complexity, but this is open if someone comes up with a simple, like W types are very, very simple specification, and index W types as well, while this is much more complicated.
For quotient inductive types?
It's as difficult as inductive. There's no big step from here to here. Here there's another big step, because for this you need infinity categories to describe these, and we don't really have a good technology. Yeah, but
I guess quotient indexed inductive types would still maybe.
Yeah, if indexing it fits into here, right?
Yeah.
And when we say inductive, the indexing is also included. Yeah. Okay, and then inductive recursive types were mentioned today or yesterday. They are just here. Okay, they just fit into here in most of the cases. So small induction recursion is the same as indexed induction or mutual induction, while large induction recursion, that gives lots of proof theoretic power. So we can view it as just index inductive types with some clever resizing. You can think about them this way. Yeah. But it's not this kind. It's not on this axis of complexity. Okay, and then the other general thing that I wanted to say about GOTS is that like, okay, so this is just remarks for those who know some category stuff. So for each GOT, right, we got model. We know what a model for a GOT is, and we know what a morphism is. Okay, so these models and morphisms, they compose into a category. Okay, they form a category because you can, when you have two homomorphisms, you can compose them. Those are also homomorphisms. You always have an identity homomorphism from each model to itself. It's just the identity factor. And you can define this for any GOT. There's no surprise. Like you can just do it by hand. And then you can prove that the composition of most morphisms associative. So this really, if they form a category. Okay. So then we had these dependent models. Okay, maybe you have composition and identity. Okay, you have these. Then you have dependent models. Okay, and dependent morphism. So as a teaser for the next lecture, or yeah, I say what these will be. So actually, these models morphisms give a category, and these give a family over the category. So together, these form a category with families, which is a notion of model of type theory. Okay, so there is and actually there's even a context extension which I write by triangle. Okay, so let's just see. So now I'm giving two languages. You have models which are contexts, which are objects in a category. I just said context. Okay, like at least you know what context is from the previous lecture. Then morphisms are substitutions, so maps between contexts. Okay. Composition is just, you can compose substitution. There's always an identity substitution, which doesn't do anything. Then dependent models are types. Okay. Those are what we call types. And like just like a dependent model is over some base model, it's exactly like how types are over context. And this is completely precise what I'm saying. And what are dependent morphisms? They are the terms. So for any GOT, okay, and then this is context extension. So what is this context extension? Let's think about this. We take a context and a type and we get a new context. So we get a model. Let's say gamma is a model. Then we have a depth model over gamma. And then we get a new model. How do you make a model and a dependent model into a model? What would you do? Well, morphisms don't help here.
Sigma.
Yeah. So you just take the sigma type. Like wait, here was the dependent model. This TMD was a dependent model over the syntax. So we can take the sigma. So we get a new model, chi m, okay, which will be an AI in chi I together with a chi d of A. Okay. It's a sigma type, and you can do the same for terms. And then the operations you do it pointwise. It's like products. Right? Actually, when you are doing this categorically, you say that we have models. You can do two models. If you have two models, you can just take the product of two models, where the carrier will just be the product of the carriers, and all the operations are pointwise, and you can put the equations. You can always do this. But now we have the dependent version of this, and this is just context extension in this type theory. Then you have substitution. In type theory, we also have substitution. It's usually written by square brackets. So you have some type, and then you have some morphism into that type. Then you get a type over a different context, right? And this also works if you have a dependent model, which depends over, so here is the dependent model over some base model. Then I know how to go from delta to gamma. Then I can substitute this dependent model so that I get something over delta. Okay, and so on. So these models and morphisms, like these models of algebraic theories, they are collected into a really nice structure, which is model of type theory. So model of type theory, I mean, we like type theory, so we also like models of type theory. So, okay. And then, okay, then I just say it more informally that actually this type theory has lots of stuff in addition to just being a model of type theory. For example, it has a unit type. What do you think the unit type is in this type theory? Okay, no, sorry, before the unit type, there's the empty context. Okay. If there's context extension, there must be the empty context. So what is the empty context? Here is, in type theory, we have empty inflow. What is empty context in the category of models? What do you think?
The model with the empty carrier.
The model of the empty carrier, that's an idea. So what do we have? What do we know about the empty context? It has a universal property, which means that from any context, there is a unique morphism into the empty context. But if it's the empty carrier, then we cannot come up with a morphism into the empty carrier. Moreover, for example, for monoids, there's no model with empty carrier, so that's not good. So that doesn't exist for any. Now I said that this kind of thing works for any thought, so it has to work for monoid, yeah? Okay, very good. The next suggestion, what is the syntax? Okay. So, do you think there's always a unique homomorphism into the syntax? It's the other way. You remember, we can go interpret the syntax outside. So, what is the empty context?
The carrier should be the unit type.
Yes, that's it. The carrier is the unit type, right? There's always the trivial model. Any algebraic theory has a trivial model where all the different carriers are just the unit type. And then all the operations are just constantly the element of the unit type. And because the unit type is one element, all the equations go. Okay. Okay, very good. You said syntax. We discussed that here. Every algebraic theory has a syntax. So what is the syntax in the world of now we translate from the algebraic theory, from algebra to model of type theory. So what is the syntax?
Unit type.
No, is it a type? So what sort of object is it? It's a model, right? So it must be, what are models? Oh, they are context. So there's a context, yeah?
Maybe a context with absurdity in it, something?
Context with absurdity, that's good intuition. So the initial object is something from which it is easy to go out, right? And if you have an element of the empty type, it's easy to go out, right? Yeah. So it's just the initial object in this category. Maybe that's one way to say it. So this is a special model of type theory, where in the category of context, there's always a terminal object. So there's always this empty context into which it's very easy to substitute into empty, right? If you want to substitute into empty, you don't need to give anything. But this is a special model where you also have a particular object, maybe actually, it's a context, right? From which there is a unique morphism, unique substitution into any context, right? So this is a model where you can go into any context. Okay? If you are able to come up with an element of this, then you are able to go into any context. Okay? And then this model also has, then it also has stop times. As some people mentioned, it also has sigma types. It also has equality types. Okay. It also has sum types. Okay. It also has quotients. So it has lots of stuff that you could call a model of typing. What it doesn't have function space. Okay. So that doesn't make sense. But let's see. So this was taking a model and the dependent model over it, and you get a new model, which is like pairing. And this is sigma is just the dependent version of it. So if you have a dependent model, okay, and then another dependent model which is dependent even over the previous one, then you get a new new dependent model. So that's just a more dependent version of this. While top, where is top, is just like this, but it's a dependent model which doesn't care about the base model. It's just constantly the unit. And equality is more interesting because you have two terms actually. So two dependent morphisms. And then there is a dependent model which expresses that those two dependent morphisms give the same result for every. Yeah. And this is a dependent model. So it's a bit harder to think what this is in terms of models. But once people start playing with models, you can use this language and it is. Oh, okay. So it is very useful, for example, you can prove that induction is equivalent to initiality just using this language for every algebraic theory. Because, so I only showed this kind of stuff by examples, right? I showed that here is particular algebraic theory, here is how to compute what morphism, right? And now I think you should have enough examples that you should be able to believe that that this can be done for any algebraic theory generically, but actually all of this can be done completely generically for any algebraic theory, because, okay, at the next lecture, I will show you what is a formal definition of a generalized algebraic theory, and that will also be a language, okay? So it will have a syntax and an induction principle, and then how do you show all of this generically for any algebraic theory? You just do induction on the language. It's just a simple induction where you interpret a type in this language or a signature in this language with all of this stuff. Okay, and yeah, but it's quite a lot. So it's a big technical work, and it's not yet clear how to organize it very, very beautifully so that you get a really concise way to show that you have all of this stuff. But okay, and yeah, so I think that the time is over. But shall we look at maybe just as a quick application of this? I just give an idea how to, that initiality is equivalent to induction. Okay. So now we work in some model of type theory. You don't really have much intuition about this model, but I mean, here if you have, right, for example, if I write Tm gamma A, A is a Tm gamma A, okay, this is the same as this. Okay, so when you write this, you think about it like this, using the notation from the previous lectures. And then I say I initial, it means that, well, for every gamma context, there is a substitution from I to gamma. Okay. Moreover, if I have gamma 0 and gamma 1, which are substitutions from I to gamma, then they are okay. This means that I is an initial object in this category, or I is initial and weakly initial and unique. There's only one, okay? And then what is induction? Induction, I has induction. It means that for any A, which is a type for I, we have a term from I to. So I said, what was induction? For any dependent model over the syntax, there is a dependent morphism from the syntax into that model, okay? Now in this language, we can write this, and so the exercise is using that this implies this, and this implies this. And if you combine all of these features, you need sigma types and equality. So this equality has equality, supports equality reflection. So it's quite easy to come up with equations like this, okay? Yeah. Okay, and there's one more component that I forgot to say. We also have democracy. So actually, this is a democratic model of, which means that every context can be turned into a type, right? We already discussed this. What does it mean that context can be turned into types? Models can be turned into dependent models in a trivial way that you just ignore other. Okay, so it took 2 lectures to to explain dots, but maybe it was useful to do it slower rather than fast. And then next tomorrow morning already, very early in the morning, we will do SOGATs. Okay. Yeah, and that's it.